Section 2.2 discusses the mass spectrometer and how we get all of those values that we get when we're dealing with the isotopes and the relative abundance of those isotopes. So we did all of those average atomic mass equations in the last unit, Section 2.1. This is the way that scientists get this data. So the purpose of the mass spectrometer is to separate particles based on their masses and then determine their relative proportions or their relative abundance. Those were those percentages that we were dealing with. So this is all dealing with isotopes. As a reminder, isotopes are looking at a specific element like sodium, which we know all sodium have to have 11 protons because that's its atomic number, but they can have varying masses. Maybe there's 11 neutrons that go with it to give it a mass of 22, or maybe there's 12 to give it a mass of 23. And so we get that average mass of sodium, that 22.999707. We get that number because each of those isotopes are in a different abundance. So how the mass spectrometer works, first of all, it has to be put into the vapor phase. So step number 1 is to vaporize. And then once we're in the vapor phase, we're able to release this very slowly into the machine. Once it's released into the machine, the vapors are ionized. So they become cations because we take electrons, we shoot electrons at these vapors, at these gases. The electrons repel off all of the electrons that are around the nucleus, and we just have these positive nuclei now traveling through the machine. And we know that we need to focus on nuclei because the majority of our mass comes from the nucleus. The mass of the electron is practically negligible. Once we have these cations, we can accelerate it through an electrical field, and the strength of this field that we have is set by the experimenter. They kind of anticipate what they're going to be looking at, and so they can refine where they want these things to end up hitting in the very end. And then after it's accelerated, the masses are going to start landing on detectors in various places. The greater the mass there is, the less deflection there is. So again, if we're looking at those sodium ions and we have some that are at 22 and some that are at 23, my mass of 23 means that it's not going to get deflected very much. So its path is not going to turn as much as the smaller ones. That 22 is going to be deflected more. The last step of this process then, as these cations hit these detectors, there's an electrical current that goes through these cations to neutralize the charge so that they're not positive cations anymore, and the more particles that are present with that mass, the more charge is required to neutralize them. So if I have a bunch of my 23s and not as many of my 22s, again looking at sodium isotopes, then I'm going to have a more predominance of the 23s, and it's going to take more charge to neutralize all of those mass of 23s. When you're all done, when all is said and done, a graph is spit out at you from your computer. It analyzes all of this data and spits out something like this, and it tells you the natural abundance of the isotope, so that's the y-axis, so the percentage of it, and the x-axis is the mass at those different ions. Now this one is most likely either a mixture or it's a organic molecule, something else that's shot in here that broke up into different parts. Otherwise, our values down here would be much closer to our values that are over here, or vice versa. And we can use all of this information to determine the average mass. Or if we were doing organic chemistry, we would be able to look at the ways that the organic molecule itself would break up into parts and figure out what functional groups you have. So if you have a hydroxyl group or an amine group, and then figure out what type of molecule you have. This one, if we were looking at the average mass, we'd have the percentage in decimal form multiplied by the masses, and then we'd add them all together to get our final value.